Scheduled for this week, we have very exciting and important things coming up. We have an assignment due tomorrow. How are people doing with that? Feeling doable? Any questions that I can answer in a class setting that everybody might have questions about that might be useful to go over? If they're more individual, did I do this right? Am I on the right track with this? I can handle those mostly in office hours, but if there's we didn't really go over this concept or really clarify this particular concept, that's something that I think everybody would benefit from.
So just writing a DFA for something is enough to prove that it's regular?
Yes.
Okay.
Yeah, but you can do that either by hand or you can use any software that you'd like. If you'd like to use LaTeX, you're welcome to use LaTeX. If you want to draw it out and take a picture of it, just make sure that you combine any typed work with any handwritten work in some way that is useful and easy to tell what answers what question. Compile it into a single PDF in the order that it's assigned so that the grader doesn't have to figure out what problem is this, which page comes first. Those kinds of questions are what usually lead to frustration. The grader be like, I can't grade this easily. But yes. Other questions before we get started with new content? All right. How was it to attend remotely? This is the kind of the first time this quarter that's happened. Was
It
that
was pretty easy, wasn't too hard at all, honestly, just like it used to be.
yeah, aside from the 360p camera we have in here.
Yeah, I was gonna say the quality is a little on the lower side.
Yeah,
But
it's very low.
Yeah.
I can't even watch it back. It's so gross.
and sometimes it's a little hard, but with the slides and with all the context of you talking and stuff, it's pretty easy to follow along.
Yeah, if that's ever the case, feel free to either post live, like your handwriting's too small, or I can't read what's going on. Any live feedback like that, like you're one of the students in the class. This is true for anyone who ends up attending remotely at any point this quarter. Let me know if I'm not doing something that's easy to tell from remotely, because obviously I don't see that. It's in higher quality here than it is there, which thanks IT, I guess. Thanks Eastern. All right, so here's what we covered yesterday at the very end. We were doing some practice problems, solving for some regular expressions and coming up with them. Any questions about what we covered before we move on to new things about this answer that we derived for any string that contains at least one pair of zeros? Pair of zeros that are adjacent to each other, I should say, consecutive zeros.
Can you just do a brief rundown of the notation again?
Yeah. Where was it? Somewhere. So we have the plus for a union, dot for concatenation, superscript star for star closure, superscript plus is a shorthand that we allow for positive closure. So I will always allow the superscript plus, even though it's not needed ever. It's just nice because otherwise it becomes arbitrarily or unnecessarily long. So we had primitive regular expressions, so we can still use lambda representing the empty string. We said we can make compound regular expressions by unioning two regular expressions, concatenating two regular expressions. So you start with primitive regular expressions, and then you can build a compound expression based off of any of these rules for what you can do to them. And we found that we could break down regular expressions into their components to kind of show equivalence between sets and languages by manipulating the regular expression of one into the regular expression of the other. Let's see, I think that this, no, So that's where we're headed now. Any other questions about the notation? That was probably way too fast. Trying to figure out where we were as well as answer the question. But do we feel like we have the notation down? We have parentheses that can combine things together for unary things like star closure. So union requires a left side and a right side, concatenation, a left side and a right side, but star closure is a unary operation, meaning it only takes one thing. It's something and you star close that. Which is why we need parentheses around something so that we can add that unary operator to it. So an expression for the language, no pair of consecutive zeros. And this one is significantly harder than the last one. And I have two solutions. There are more. The question is just, will I be able to determine whether yours is correct or not? Sometimes it's hard to find that counterexample. Yeah, feel free to work in pairs if you'd like, because this can be a bit of a challenge. No pair of consecutive zeros. Hopefully people didn't see too much of the answer. A quick review of what we covered last time, and now we're on to generating a more difficult regular expression. No pair of consecutive zeros in binary. If you think you have an answer, think very critically about whether it handles all cases. Things like, can your string start with a 0? Can your string start with a 1? Can your string end with a 0? Can your string end with a 1? Does it allow for multiple zeros? Working on an answer, talk to your neighbor. Walk through the logic that you've come up with so far. And see if you can combine your ideas into an answer. This one's tougher, isn't it? The question is it so tough that it's not regular? What would that mean for a language to not be regular?
Just not be expressible with regex.
Yeah. Is this expressible with a regular expression? The answer to that question is yes, it is expressible with a regular expression.
So you think that's your. Options.
Still stumping people. I'm proud of myself.
So. But I just want to make sure that there's not zero. So it's, you know, oh, you're right, sorry. Just, what I'm concerned about is if this is you just happen to pass, is it was. Like what we wanted to just like. This is your. Isn't possible. Possible. And so. As it says. Just be zero. Okay.
To get everybody kind of on the same foot here, I have an answer that is a bad answer because it doesn't work for two kinds of strings. Strings ending in a zero and strings consisting of all ones, but maybe this starts to get you in a direction. Because we know that any zero has to be immediately followed by a one or be the end of the string. That substring that has to be preceded or succeeded by an arbitrary number of ones. And we want to be able to repeat that logic. So how could you change this existing expression to consist of strings ending in a zero or consisting of all ones? So those are the big weaknesses. Ring zero. Yeah, but it's the string, the string, the only character of the string is zero. That is a string that has no consecutive zeros. I would argue that is not possibly your expression. A good start. I think you're close.
Can you check this one?
Yeah. Always had this zero bond, start with one. So there's no way to start this giving definite zeros with that or one of those. Does not allow for any consecutive zeros. And it allows for any arbitrary number of ones in a row. And zero surrounded by ones at one point and zero and discriminant zero.
Zero. Times that.
Get the outer star here, you choose
Yeah.
this or that, so.
Curious this.
Start with zero.
So the idea is I want this to be just like the main function, this kind of the edge case, but it's to zero.
Right, and now it allows it to end at zero. It allows for the string its own at zero.
Can't do zero.
Start with zero. No way to come back with this. So close. So
Every day
close.
Messy.
So some of them are messy. This is so the design of these first bullet points here is meant to lead you to a longer answer, and then a shorter answer does exist that I will also go over. But I feel like this answer and the longer answer that I'm about to go over is more of an algorithmic construction. So how would you modify this incomplete answer to consist of these things? What could you add to this? Rather than trying to reinvent the wheel, take this as kind of a baseline. The only weakness this has is strings ending in 0 and consisting of all ones. How could you use regular expression syntax to have this potentially end in a 0? What would you add to this to either make this end with a 0 or not? What could you add to this to handle strings that consist of all ones? You think they have an answer to one or the other of those? Yeah.
The 0, you just wrap the whole thing in parentheses and add a union 0 at the end.
That's it's pretty close to what I ended up doing. I ended up concatenating it with either a 0 or a lambda.
That sounds like adding a lambda to it, I don't know what that means.
It basically makes it optional. A way of saying you could include this at the end, but you don't have to. So let's give you the answer. You've been working on this for quite a while. So here is kind of what I constructed as an algorithmic answer. So we can either choose the base case or the string that is meant to consist of all ones. To add a 0 or lambda at the end basically says, all right, we take this and allow it to end in a 0 or not, because we know that every one of these must end in a 1. This has to end in 0, 1, or some number of ones. Either case, this ends in a 1. So to allow this to have a 0 at the end of it, we just allow, regardless, the 0 to come afterwards, or not. If we do this, then it ends in a 0. If we do this, then it ends in a 1. It doesn't allow us for the strings that consist of all ones, because this forces there to be at least one 0. So this handles the string of all ones, but what about the string that's all ones with a 0 at the end? Because just like here, we have that same weakness right here, where we can't consist of that one string, one language, a bunch of ones followed by a 0. So this allows for that.
You also, just about 1 0 1 0 1 0 1 0.
Yes, so this is so like 1 0 1 0 1 0 1 0. Here's where the first 1 0 1 is going to come from. Is in this repetition, so that's going to be that. Then we loop here and allow the 0 1, that is that 0 1. loop here for the 0, 1, that is that 0, 1, and then end it in a 0. A great potential counterexample. So we certainly need to have a path through this that generates anything.
Also work for.
I think the feeling that the answer is no. But I'm struggling to find a counter. Actually, I have to look at it longer to be able to find an accurate counter here. But so if it's not right, then it is very close. Yeah, I like what I'm seeing. I think we're getting a little bit more of an intuitive understanding of how to construct a regular expression, because I can tell you the rules all day and it's boring, but actually giving you the problems to work through to generate these for yourself, you start to understand how the constructs can work together to be able to kind of abstract the language. Because when you're thinking at the compiler level, when you're thinking at the programming language level, there's a lot of abstract thinking that's going on. Being able to take all of these examples and abstract them to an expression that maps to all potential strings that adhere to certain rules. That's exactly the kind of thinking that you need. So how could we shorten this? Is there a shorter version that also solves the problem? So some alternative reasoning, the language is a repetition of any string 1 or 0, 1. Right? These are the allowable substrings in any non-consecutive zeros. Really, if you break this down into binary and you have strings that are either 1 length or 2 length, we don't want to allow 0 because we can't repeat that. 1, we have 0, 1. Yes, we should do them all. We have 0, 0, 0, 1, 1, 0, and 1, 1. And we just straight up don't want to allow repetitions that contain the 0 or 0, 0. That's straight up not allowed. And we don't really want 1, 0. Like, what subset of these would be able to produce a string that doesn't have pairs of consecutive zeros? If you allow both 1, 0 and 0, 1, you can put them next to each other. You have to get rid of at least one of those. And this can be produced by that being repeated. So we don't need this. We have to get rid of one of these. So I get rid of the 1, 0. And now, between these two, we can produce anything, any arbitrary length without the pair of consecutive zeros, without needing to consider strings of length 3. So if we do that, then we can come up with something like 1 or 0, 1 star. But this doesn't, again, allow strings to end in 0. So we just concatenate it with that same 0 or lambda to allow it to end in a 0. So thinking about it as a binary string of chunks of certain lengths of at most something might help you get there as well. This is significantly shorter than that. There's no union outside of a. Like, this is saying there could be strings in multiple different classes that could belong to this language. The shortest answers usually don't have those. Okay, there's only a single class made up of a component and an optional component, a repeated component and an optional component. So those are kind of the reasonings and thinking out why that might lead you to a couple of answers. And of course, both answers are correct. So we can have equivalent regular expressions. If they denote exactly the same language, then the regular expressions themselves are equivalent. So we can say rules that we know, for every regular expression, there exists one and only one regular language. If you care about any of these proofs, feel free to read the textbook. This class would be way too long if I went through all of these proofs, but I think that that's pretty intuitively apparent. If you have a regular language, it denotes exactly one language. It can't denote multiple languages. For every regular language, there is at least one regular expression that can denote it. It can describe it. Oftentimes, there are multiple. If there are multiple, there are infinite. Union lambda, union lambda. All right, concat with lambda, concat with lambda, concat with lambda. So how would we go about doing this? I'm not going to go through the proof, but we could construct an NFA that accepts the language that is represented by a regular expression. So could we parse a regular expression to be able to create an NFA for it? For part two, generate an expression generating all labels from all walks of an NFA from the start state to any final state. So you could start to think of, all right, how could we reach any set of these final states and have denotions for the characters that are consumed to get to each of those final states? And that will produce the expression for you. Of course, there can be cycles. If you can traverse that cycle, you can traverse them arbitrarily in any order. So that leads to all sorts of fun that we don't really want to get into at this point. So this could be something that if we have time at the end of class, we can come back to if people find this concept really interesting and want to dive into the graph theory of what is a generalized transition graph? How can we show that we can construct a regular language from an NFA? That's something we could dive into as something to explore. My best guess is we won't have time. There's just so much to cover in this class, and I think the time is best spent diving into more of the applications of compilers. And because we'll only get about 2 weeks at the end of the quarter when we can talk about compilers, there's so much preliminary work to do. It should be a 2-course sequence. But if this is really interesting to people, something we can come back to. Questions on this? I think the main takeaway from this slide is that there are equivalences and there are reasons behind those equivalences. All right, that's the extent to which we're going to cover regular expressions. We're going to go into regular grammars. This is the last relatively easy topic before we hit our first major roadblock of the quarter that we will probably spend a week on because it's tough. So enjoy it while it lasts. Tomorrow will be a very important class. All right, we've talked about 2 different ways of expressing regular languages. We have finite automata, DFAs, NFAs. We now have regular expressions. We can also use grammars. So what was a grammar? We use symbols from the alphabet. If that's the case, we call them terminals inside of a grammar. That says that of the productions that we are applying, we are looking for and expanding into the actual character as part of the string. Non-terminals you can think of as variables. Those variables represent more complex structures than just the primitive character in the alphabet. So we go some kind of non-terminal on the left to some number of terminals and non-terminals on the right. And those specify how can we expand this variable into some sequence of variables and characters from the language. After you've expanded every variable, all you're left with are characters from the language, and that represents one possible string that could be in the language, or that is in the language, defined by the grammar. So I like to think of terminals as primitive variables, like an int or a double, something that can't be reduced more in a programming language. That's how they are used in a digit, a character, something that is irreducible. Non-terminals are more like objects. They're composed of either other objects or primitives. So you can break down the structure of any program in an object-oriented language into primitives, but we allow for objects to group those primitives together in some way that makes sense to us. So a person is a grouping of an integer age and a double GPA and a double salary and whatever else you want to, and an object address, and it's a composition of all of these things. Some of those are primitives and some of those are other objects. So think of a grammar kind of like that, and it will tie to some of the constructs that you use when you use an OOP language to write a program. So objects can be made up of other objects and or primitives. All objects eventually have to be broken down into primitives. You can't have an object that does not break down into primitives somehow via some sequence of breaking it down. So a regular grammar is just like a grammar that we've seen before. Nothing new is going to change, aside from we're going to place some additional requirements on the structure of your productions. That's going to be, it has to either be right linear or left linear. A right linear grammar can have productions in one of two forms. Every non-terminal, every production has to be a single non-terminal on the left-hand side, followed by, so this is a single character in the alphabet, followed by a non-terminal, single non-terminal, or a non-terminal into a single character. Sorry, not a single, it's a string of terminals. We'll go with that. So X, if we're in the language binary, could be 10010 followed by a B. And then that B can be a non-terminal that expands into, 1, forcing it to be end in a 1 or something of the sort. So strings of terminals followed by a single non-terminal. We cannot have multiple non-terminals in any production, right-hand side of any production. And we cannot, in a right linear grammar, have that non-terminal come before the string of terminals. So when you see right linear, think of it as the position of the non-terminal in the right-hand side of the production. Where is this capital letter? This capital letter is on the right in a right linear grammar. As you might guess from this description, left linear is exactly the opposite. Left linear, the non-terminal comes before the string of terminals. So where is that capital letter in the production? In a left linear grammar, it's on the left. We can still have an arbitrary number of productions. They just all have to adhere to one of these two forms. Non-terminal, and if it's left linear, non-terminal to non-terminal string of terminals, or non-terminal to string of terminals. Single non-terminal allowed on that right side. Let's see an example. So here is a linear grammar. Remember that we always start our first production with the non-terminal S that denotes this is where we start. If we want to produce a string, we start with S. So first and foremost, analyzing this, is this grammar left linear or right linear? Left linear. What is a string that could be derived from this grammar? Argue AAB. What are the sequence of productions that lead to generating this? So we start with S. We have to replace S with A, B. What do we replace this A with?
A B.
A B?
Capital.
What do we replace that B with? There's only one option. So that is the sequence of productions and applications that lead us to the string that's in the language.
This language is just repeating. Every time there's a beat, it has to be a before or after.
What's another string that's in the language? Yeah, so we could do just like before, A, B, but now instead of replacing A with a B, we could use this production instead. So now we have this A, B, that replaces this A followed by the AB. Now we'll replace this A with a B. Replace the B with lowercase a. This is also in the language. You can see that really there's only a branching factor of 2 here. So the question is just how many times is this A looping here before we go into a termination? So all that's different between this and this is that we've added the suffix AB to the end of it. Each time we loop through this production an extra time, we're just adding an extra AB to the end of the string. So this is all strings that start with AAB and end with an arbitrary number of ABs. What would a regular expression be for that language?
Would be AAB, it's our closure of AB.
So we want AAB, and there's no other way to produce anything shorter than that. Do we agree? We want to concatenate that with AB star. So that's not really an algorithmic process, but you can start seeing about how you might intuitively ask, what is the pattern? What is allowed by this grammar? Then you can start thinking about applying that pattern into a pattern recognition kind of expression. All right, so I've done exactly the same thing here, just to give you an example of one of the strings. We know that string is in the language defined by the grammar. Next example. Left linear or right linear? The question is, the answer is neither. This grammar is not a regular grammar because we have 2 productions here that contradict. This one is right linear, this one is left linear. So we cannot have a grammar with both types of productions. They all have to adhere to one or the other, not both, not neither. So this grammar would not be a solution to a problem that asked derive a linear grammar for a particular language. You would need to come up with something that only uses left linear rules or only uses right linear rules. Yeah.
Is that only for regular grammar or all grammar?
Only regular grammars. We will relax a lot of these restrictions as we talk about other classes of languages later in the course. This is kind of the most specific, interesting language class that we are going to talk about. We will reduce that as we start talking about what kinds of languages can exist and what is the power of those languages, what can we do with them?
So why is it not, so why is it not a regular, like, why can't you just, like, combine it?
You could kind of combine, I'm sure you could convert this. It may still represent a regular language. But to be able to prove that that can be done, it should be writable in a way that is left linear or right linear. The issue here is that we kind of can. Well, let's take a quick aside and talk about exactly what a left linear or right linear grammar is doing. We talked about why DFAs and NFAs represent regular languages, I think, right? That with that concept of there were a finite number of states and to not be a regular language. Or to be able to do this, we had a finite amount of memory, basically. So to generate these kinds of strings, we need to be able to parse them from left to right or from right to left. We need a sequence of rules that can generate, yes, we can generate an infinite number of strings or strings of an arbitrary length, but we need rules that can generate them from left to right or from right to left.
Check this out, so we did it from the previous step.
Right.
Okay.
Yeah, so it's a repeated application of the same kind of rule that adds characters to the end of it or adds characters to the beginning of it. And that allows us to apply the rules to parse the string if it's arbitrarily long in one way or the other way.
This just lets you go in circles, that's why you can't.
Yes.
Do it.
Yeah, this allows us to go from A to B, adding at the end, and B to A, adding at the beginning, which allows us arbitrary middle insertions, which we can't allow in a regular language. Yep, so that's kind of the why behind these rules. We can talk a little bit about constructing automata from grammars because this is a little bit easier than every other conversion that we've talked about so far. So let's assume we have a right linear grammar with the following productions. And I'm going to start using a little bit different names here because this will become apparent momentarily. So here's our grammar. B0 will lead to the terminal A followed by the non-terminal B sub 1, B sub 1, AB followed by B sub 0 or B. So this is right linear because all of the variables, the non-terminals, appear on the right side of their associated productions. Each one of these three productions adheres to the rule of terminals, non-terminal, terminals, non-terminal, or the type of rule terminals. So this is a perfectly legal, regular grammar. The reason I use these non-terminal names is because they're going to represent vertices in our finite automata. So we will start with states representing each non-terminal. So B sub 0, B sub 1. We're going to add a new state representing the final state for completed derivations. So we basically are just now, let's make sure that I'm not going to overwrite this. Let's do it up here. We have B sub 0. We have B sub 1, and we have B sub F. That is going to be a final state. Whenever we could transition to something that terminates a string in this grammar, we will transition to this final state. So what is needed in order to get from B sub 0 to B sub 1? An A, we need to read an A, and then we are at B sub 1. So yeah, this becomes kind of the transition for this. So first production tells us there's an edge labeled A between B sub 0 and B sub 1. So we're going to do that, draw edge with an A. There's an edge labeled AB between B sub 1 and B sub 0. This is not quite the same as we have done historically. We can only consume a single character in the input going between two states, but it would be easy enough to get a mid state to this, right? So we could make a B sub 2 that consumes the A and make a transition from that back to B sub 0 that consumes the B. So let's do that real quick. Let's add a B sub 2. This does this on an A and this on a B. Right? This allows us to go from B sub 1 to B sub 0 on an AB. That's exactly what we've done. Since we can't have an edge of multiple characters, break them apart. New state in between them. Second part of the second production says that there's an edge labeled B between B sub 1 and B sub F. Because whenever we make that decision, we transition into B sub F for that final production. Now, note that we said this is an NFA. We didn't say that, did we? We said it's a finite automata. If this needed to be a DFA, then we'd worry about other kinds of transitions. But as an NFA, this is perfectly fine. We don't need to specify all the transitions. We don't need to consider a trap state. Are we out of time already? These classes fly by. They're so interesting. So yeah, basically we have a solution that looks exactly like what I just drew. And we don't need trap states. We don't need anything else. This is just a perfectly complete NFA. And we'll come back to this tomorrow. And we will probably start the pain. Very important class. I will see you then and try to make it as painless as possible. I have office hours starting now. If you have any questions about the current assignment, studying for the exam, if you haven't taken my exams before, they're a little brutal. Study hard.
Thank you, Professor.
Thank you.